Welcome to Weekend Academy. We are going to see in chemistry coordination compounds and their geometry, shape, and hybridization, and many more things about the coordination compounds. A coordination compound is a type of compound in which at least one coordination sphere is there. In a coordination sphere, there is a central metal atom or ion. Central metal atom or ion that is located at the central metal atom or ion surrounded by a fixed number of species called ligands. Ligands are nothing but a neutral atom or a molecule, negatively charged ion or a molecule. Example Cn minus, NH3, even Cl minus, like that. H2O, these they are called ligands. What do they have in common? They are capable of donating a pair of electrons to the central metal atom or ion and thereby form a coordinate bond. I say again, these species are called ligand. They are capable of donating at least one pair of electron to the central metal atom or ion so that they form a coordinate bond by donating electron. Is that okay? Now, central metal atom or ion may have central metal atom or ion has primary valency as well as secondary valency. Primary valency is nothing but formal charge it carries. Say for example, nickel 2 plus. I'm sorry, Ni. Nickel 2 plus. This 2 plus is called primary valency or formal charge. And the same nickel has one more valency called secondary valency, and it is 2, 4, 6 like that. It is nothing but the number of ligands surrounding the central metal atom are said to be secondary valency. In other words, the number of coordinate bonds present in the coordination sphere, the total number of bonds is said to be secondary valency. It is otherwise called coordination number. This coordination number usually 2, 4, 6 like that. Here we are going to see 4 and 6. Suppose the coordination number is 4. The hybridization is sp3 or dsp2. If the hybridization is sp3 tetrahedral in shape, dsp2 square planar. If the coordination number is 6, it means this is example. There are 6 ligands surrounding the central atom, and hence this particular example coordination number is 6. This is due to sp3d2 or d2sp3 type of hybridization. But this hybridization giving rise to the structure or shape called octahedral. Okay, so a coordination compound consists of a central metal atom or ion surrounded by a fixed number of ligands, and these ligands are called secondary valency of the central atom. The charge carried by the metal is called primary valency. We shall discuss in detail one by one with certain examples. Here is the first example, tetracyanonickelate 2 ion. This is the IUPAC name of this complex ion. This is represented by NiCN4 times 2 minus the net charge. Here nickel is the central metal ion. Cn minus or the 4 Cn minus are said to be ligands. So the nickel atom has a formal charge. How do we find out the formal charge? Each cyano group has 1 minus charge. There are 4 cyano group, therefore 4 minus. Okay. The net 2 minus are left here. So 2 minus is gone. Then how much? The net 2 minus is inside. The 2 minus is neutralized by nickel. Therefore, nickel should have 2 plus. Nickel should have 2 plus. So, the central metal is nickel 2 plus. Ligands are Cn. Primary valency or formal charge of the nickel is 2 plus and its coordination number is 4. Okay, now actually I am coming back to the topic again. Tetracyanonickelate. Why do we use the word nickelate instead of nickel? Because as per the IUPAC rule, when a metal is present inside an anion, negatively charged ion, the metal is called as nickelate, copperate, iron, ferrate, cobaltate, and so on. We don't call it as nickel. That's why, as per the IUPAC rule, this complex ion is named as tetracyanonickelate 2 ion. 2 is the formal charge carried by the nickel atom. Okay, now come back to the electronic configuration of the nickel 2 plus ion. Nickel 2 plus ion 3d8. Those 8 electrons in the 3d shell are distributed as per the Hund's rule. First 3 orbitals of the d shell have 2 electron, and then fourth and fifth d orbitals occupy 1 electron each. Okay, this is the nickel 2 plus ions electronic configuration. But a very strong field ligand Cn minus, what does it do? It pushes the electron from here to there and thereby make the fifth d orbital vacant. That's what happened here. And thereby the one electron is pushed inside and we have four pairs of electrons and one vacant d orbital in the 3d shell, subshell. Okay, then the d orbital is now available. The vacant d orbital is now available for hybridization. Take this d orbital and next 4s orbital 1 and 4p. From 4p orbital it takes 2 orbitals. Altogether 4 orbitals are mixed up together and we get 4 hybrid orbital. They are called dsp2 orbitals. dsp2 orbitals equal in energy, equal in shape. They repel each other and thereby they stand at the 4 corners of a square. They stand at the 4 corners of the square and giving rise to the geometry square planar. From the beginning, it is because of the Cn minus ligand, which is strong field ligand, which pushes one electron inside and thereby one d orbital is made vacant. You make use of this d orbital and mix one d orbital, one s orbital, 2p orbital together, dsp2 orbitals, 4 orbitals. These 4 orbitals repel each other and go stand in such a way they occupy 4 corners of the square. Then each cyano group give one pair of electrons in and takes the position of all the 4 dsp2 orbitals. And this is how this complex compound ion is formed. And when we come to the magnetic behavior, it has no unpaired electron. But actually in the ion, there are 2 unpaired electrons. Unpaired, lone, separate, one electron. But what happened? Because of this pairing up happened, no unpaired electron in this compound. It is a diamagnetic compound, which is experimentally proved. Experimental data gives the supports that it is diamagnetic. No unpaired electron, diamagnetic, hybridization dsp2, thereby square planar shape. Now we shall pass on to the next example. Here is another example of the same nickel tetrachloronickelate 2 ion, which is an anion represented as NiCl4 2 minus. Again, the former charge on the nickel can easily be found 4 minus 2 minus left. The other 2 minus cancelled by nickel. Therefore, nickel supposed to have nickel 2 plus charge. Its electronic configuration 3 paired electrons, 2 odd electrons. Thereby, 3d8 electronic configurations just like that with the 2 unpaired electrons. Now, a weak ligand. How many weak ligands are? 4. There's a coordination number of nickel here is 4. These 4 chloro ions donate one pair of electron, and those electrons are occupied in the next 4 orbitals, 4s and 4p. One orbital from 4s, 3 orbital from 4p. Thereby, all these 4 orbitals mix up together and we get sp3 hybrid orbital. These sp3 hybrid orbitals, all these 4 orbitals repel in such a way they occupy the corners of the regular tetrahedron. Regular tetrahedron. If you draw a tetrahedron diagram, these are the 4 corners. In each corner, 1 Cl minus occupy at the center nickel 2 plus ion is there, thereby giving rise to the hybridization sp3 shape tetrahedral. When we see the magnetic behavior, there are 2 unpaired electrons in the 3D subshell of this nickel of the compound, and hence the compound is paramagnetic due to the presence of 2 unpaired electrons. Unpaired electrons. Due to the presence of 2 unpaired electrons, this compound is paramagnetic in character. From the beginning, tetrachloronickelate ion. Why nickelate? Because it is in the anion. Okay, primary valency or formal charge of the nickel is 2 plus, and its electronic configuration is 3d8 with 2 unpaired electron. A weak ligand Cl minus without disturbing the 3d orbital occupy 1 4s orbital, 3 4p orbital. Altogether sp3 hybridization takes place. As a result of it, tetrahedral shape is obtained, and the compound with 2 unpaired electrons, it is paramagnetic and is paramagnetic. That's all about this. Next we shall come to another example. There is one more example now for the same nickel. Here the compound name is tetracarbonyl nickel 0. We don't use the word nickelate here, say nickel, because this is not an ion. First of all, it's a neutral molecule. In the neutral molecule, the metal is called by its own name. We don't make it as a different way, nickelate, ferrate, or like that. We say it's just nickel. Okay, the central metal atom, this is not ion, is Ni, whose electronic configuration is no 3d8 4s2. No electron is lost or gained, and therefore the atom, neutral atom, 3d8 4s2. Okay, and what is the name of the ligand? Carbonyl. Formula CO. It has no charge. It's a neutral molecule. But carbonyl CO is actually, this structure is this, and it has 1 lone pair of electron. CO is capable of donating 1 pair of electron to the central metal atom in the coordination sphere. Okay, that's why this acts as a good ligand. This species. Actually, the CO is also a strong ligand. Its magnetic field is such a powerful, it can influence. Okay, now we see the electronic configuration of this is, just now I said, 3d8 4s2. Shall we write here 3d8 4s2? 3d8 means no first 2, second orbital of the d, third orbital of the d, fourth orbital 1, fifth orbital 1, and s2 orbital 2. This is 3d and this is 4s. Okay. And 4s orbital. This is the actual electronic configuration of 3 nickel. Okay. What happens here? The carbonyl group is a strong field ligand. The strong field ligand, what does it do? It pushes these two electrons inside the inner d orbital, and thereby what happens? It becomes the 3d8 gets 2 electron from here, and it becomes a 3d10. 3d10, this is what happens. All the 5 degenerate orbitals of the 3d shell get paired up electrons. See, 10, 5 pair of electrons, no unpaired electron at all. This happens, this arrangement happens due to the influence of strong magnetic field offered by carbonyl group. We call it as a ligand. Okay, once this shifting occurred and next 4 orbitals are left vacant. S orbital is vacant, p orbitals are all vacant, and then 4 CO group donate 1 pair of electron to these 4 orbitals, and these 4 orbitals mixed up together and form a new set of orbital called sp3 orbital. These orbitals are called sp3 orbitals. They are all equal in shape, size, energy, and they are called sp3 hybridized orbital. These sp3 hybridized orbitals repel among themselves and orient in such a way, giving rise to a tetrahedron shape. The corner of tetrahedron is occupied by 4 corners are occupied by 4 CO molecules and giving rise to this tetrahedron shape. Okay, now see one more thing. No unpaired electrons, and thereby this compound is diamagnetic. It's a diamagnetic molecule. How do we come to know? Experimentally, we are able to prove that this compound is diamagnetic, and this supports the structure, this type of shipping, and all those things, this type of hybridization, all those things are supported by the practical evidence that this compound is diamagnetic and experimentally proved. And now we have to remember nickel carbonyl is a diamagnetic molecule. It has no unpaired electron and the shape is a tetrahedral because sp3 hybridization. What are the 4 points to remember? sp3 hybridization and no unpaired electron, diamagnetic, tetrahedral in shape. That's all. That's it. Okay, shall we pass on to the next example? Here is another example for nickel metal. Here, the coordination number of nickel is 6 because 6 species are surrounding the nickel. Water is a neutral molecule. Is that okay? Neutral molecule, and it does not have any charge. As a whole, this coordination sphere has +2 charge. Where does this +2 charge come from? It comes from the nickel. Therefore, central metal ion is nickel 2+. The name is again hexa aqua. Aqua is the correct name given by the IUPAC system for water. Hexa aqua nickel 2 ion. We don't call it as nickel 8, nickel 2 ion because it is a cation. In a cation or a neutral molecule, the metals are named as it is. Copper, nickel, titanium, iron, like that only we will say. This Roman letter 2 represents the charge of the central metal 2+. Is that okay? Hexa aqua nickel 2 ion. The IUPAC name we understood. Charge of the central atom, we understood the electronic configuration. We already No, it is 3d8, 4s2, 4s2, 2 electrons are lost. That's why it is 2 plus. Okay, actual electronic configuration is 3d8. Those 3d8 electrons are distributed in such a way, 3 orbitals of the d shell has paired up electron, 2 orbitals of the 3d shell has 1 electron each. So this is the electronic configuration. The ligand is aqua water. Now, since the coordination number is 6, there should be 6 vacant d orbitals available, so that 6 water molecule, each water molecule can give one pair of electrons to the central atom. So how do we get those 6 vacant orbitals? From 4s, 4p and 4d. These are the next 3 set of orbitals available in the nickel. 4s in 4s 1 orbital, 4p 3 orbital, the 4d we take only 2 orbitals. Thus we have 5 orbitals mixing up together and form a new set of sp3d2 orbitals. These sp3d2 orbitals are all equal in shape, size and energy, and these 6 orbitals repel each other, and thereby they stand apart from each other and giving rise to a particular geometrical shape, octahedral. In an octahedron, there are 6 corners, 4 corners in a square planar, in a square, and one is above the square, one is below the square, resulting to octahedral shape. Here we use the word octa. Octa means 8, In an octahedron, a regular octahedron, 6 corners are there, 8 faces are there. That's why we call it as octahedral. In a regular octahedron geometry, 6 corners are there. No, all these 6 corners are occupied by 6 ligands, say water. See, at the center nickel is there. One corner occupied one water molecule, another water molecule, water molecule, water molecule. This giving rise to regular hexagonal, regular octahedral structure. Regular octahedral structure. In an octahedron, 6 corners are there. These 6 corners are occupied by ligands. So these 6 orbitals, hybrid orbitals, not 6 hybrid orbitals, are projecting to the corners of the regular octahedron and giving rise to the octahedral shape. Okay, here the hybridization is sp3d2 and it is octahedral in shape. It has 2 unpaired electrons. That's why we call it a paramagnetic compound. This compound is paramagnetic, supported by experimental result. So what are the things we will have to remember about this compound? Hexa aqua nickelate, nickel ion is an 6 coordination number. Central atom is nickel 2 plus ion. The ligand is aqua water. The hybridization is sp3d2. And since the d2 orbitals taken from outside, it is called outer. It is an outer orbital. It's an outer orbital complex. It is an outer orbital complex, and sp3d2 giving rise to octahedral shape due to the presence of 2 unpaired electrons, which is paramagnetic. This is all about this compound. We shall move on to the next example. Here is a cobalt complex. Cobalt atom or ion surrounded by 6 ammonia. The coordination number of this cobalt is 6. 6 ligand surrounding it together, surrounding it at the center atom, and thereby giving rise to this complex sphere. How do we call it as hexaamine cobalt 3 ion? Hexa 6 amine ammonia cobalt 3 CO3 plus ion. CO3 plus ion. Is that okay? How do we come to know the cobalt has 3 plus charge? 6 ammonia molecule are neutral. Ammonia is neutral. It doesn't have any charge. Therefore, whatever the charge present on the top 3 plus is only coming from the cobalt. That's why it is CO3 plus. Cobalt electronic configuration 3d6 4s2. The 3d7 4s2. I'm so sorry. Cobalt is no. Cobalt as a whole is 3d7 4s2. But cobalt 3 plus has the 3 electrons, 7 here 1 electron, here 2 electron removed, and thereby we have 3d6. This you understand? Cobalt atom neutral has the electronic configuration 3d7 4s2. Tripositive means 3 electrons have to be knocked out. 2 from s orbital, 1 from d orbital, and therefore the net is 3d6. Okay, so 3d6 is the electronic configuration of cobalt 3 plus ion. These 3, okay, the ligand is NO3. Then the ligand what we are using here is NH3. This is also a strong field ligand. Strong field ligand. And the 3d6, what is the possibility? 2, 3, 4, 5, and 6. Am I correct? First 3 d orbitals are 2, 2, 2, and fourth orbital 1, and fifth orbital 1. This is the actual configuration of D6. I'm so sorry. D8 is, we are not talking about D8. This is D6, D6 means 2 electrons in the first, 3, 4, 5. 1, 2, 3, 4, 5. See here. First orbital 2 electron, the second, third, fourth, fifth. 4 unpaired electrons are supposed to have. 4 unpaired electrons. This is the D6 configuration. First d orbital, there are 2 electrons. Second one, second, third, fourth, fifth, all have one electron each. Okay, now what happens? Ammonia, a strong field. What does it do? It just push these 2 electrons inside, and these 2 electrons get inside and pair up, and resulting to 3 unpaired, 3 paired up electrons. The unpaired electrons present in the d orbitals are pushed inside. Who does this job? Ammonia. Why? It's a strong field ligand. By pushing inside, we have 3 set of paired electrons and 2 vacant d orbitals made available. 2 vacant orbitals are made available for hybridization. Who does this job? Ammonia. And thereby 2 d orbitals, 1 s orbital, and 3 p orbital, altogether 6 orbitals are available for the hybridization, and such hybridization is called D2sp3. 2 d orbital, 1 s orbital, 3 p orbitals altogether have D2sp3 hybridization. So this hybridization taking place in this particular complex hexaamine cobalt 3 ion has a D2sp3 hybridization. The d orbital taken part is inside. It's not going out. So only it's called inner orbital complex. And is there any unpaired electron? Unpaired electron? no unpaired electron. All the electrons are paired up. Actually, the ion, there are 4 unpaired electrons in the ion. Those 4 electrons are paired up, getting paired up by ammonia. This part you understand and know? Remember. The next is, and this is proved by experiment result. It is diamagnetic. The compound is, what is that? The compound is diamagnetic. In practically, we found it is diamagnetics. This supports this type of arrangement. Okay. And the shape is, since it is D2sp3, 6 orbitals are involved. There is only one possibility, that is octahedral. In a regular octahedron, there are 6 corners. Each corner is occupied by one ammonia molecule, giving rise to this regular octahedral shape. Now, sum up. The name is hexaamine cobalt 3 ion. Formula is CONH3 6 times. The net charge is 3 positive. Central metal ion is cobalt 3 plus. Its electronic configuration is 3d6. The 3d6 is actually 2 1 1 1 1. This is the electronic configuration of the d orbitals in free state by the presence of 6 ammonia ligand, which is a strong field ligand, which pushes up the electrons, odd electrons, and thereby making them paired up, leaving two vacant orbitals in the 3D shell. So those 2 orbitals, along with the next 1s orbital and 3p orbitals together, making D2sp3 hybridization. This D2sp3 hybridization resulting in the octahedral shape orientation. 6 ammonia molecules are occupying the corners of the 6 corners of the octahedron and giving rise to octahedral shape. The molecule is diamagnetic in nature. It is an inner orbital complex and octahedral in shape. This is all about we have to know about this compound. Now we shall pass on to the next compound of the cobalt. Hexafluorocobaltate 3 ion. The central metal is CO. The ligands are F minus. Each F minus ion give 1 pair of electron to the central CO. The charge of F is 1 minus. 6F means 6 minus. Out of 6 minus, 3 minus are left and the other 3 minus cancelled by the central metal CO. That's why its charge is 3 plus. Okay. 3 plus means it is 3d6. The last example we saw the 3 plus CO. CO 3 plus is 3d6. And the electronic configuration is the first orbital 2 electrons and the rest of the other 4 orbitals of the 3d shell have 1 electron each. This is how the 3d6 is distributed. Okay, ligand is fluoro F minus. Then all the 6 F minus ligand, when they approach, because the F minus is a weak field ligand. Weak field ligand, it can't do anything with the inner 3D shell. It cannot manipulate the electronic structure. Simply search for the vacant orbital. They take the next 6 orbitals, 1 from S, 3 from P, and 2 from the 4D subshell on the outer 4D subshell. Thereby, they take 6 vacant orbitals sp3d2 and mixing up all those 6 orbitals together and forming a newly set of orbital called sp3d2 or hybrid orbitals. All of them are equal in shape, size and energy. Those orbitals repel themselves from each other and resulting a regular octahedral shape. 6 corners are there. Each corner is occupied by F minus ligand and giving rise to this complex structure. Okay, now we shall see the number of unpaired electron. There are 4 unpaired electrons. See, 1, 2, 3, 4 unpaired electrons. Due to the presence of 4 unpaired electrons, the magnetic moment is so high, dipole moment is very high, and it is called a strong paramagnetic compound. It's also called high spin complex. Okay, it's a paramagnetic in nature with a large amount of unpaired electron resulting high magnetic moment. This is one important thing about this compound. Next, its shape is octahedral. It's all because of the coordination number 6. We know the reason for the presence of unpaired electron because it's a weak field. Which is a weak field ligand? F minus is a weak field ligand. It is a weak field ligand. Sorry. Yeah. Which one? F minus. F minus is a weak field ligand. That's why it cannot do anything with the 3D orbital and simply leave it and take the next 6 vacant orbital and mix up all those 6 happen and resulting 4 unpaired electron. Thereby it is a strong paramagnetic compound and octahedral in shape. This is all about we have to know in this example. Now we come to the another example of iron complex. Iron connected with the 6 cyano group. Cyano group is again a strong field ligand 6. Now we will have to calculate the charge on Fe 6 minus. Each cyano is 1 minus, therefore it is 6 minus 6. And the net charge here is available is minus 3. So minus 3, then how much is left? Only minus 3 inside. Wow. Out of the 6 minus, 3 minus is gone. Then how many minus charges are left out? 3 minus charges. Who balances this minus charge? Fe. Therefore, Fe is supposed to have 3 plus charge. Only then this is possible. The Fe atom is tripositive atom. That's why out of the 6 minus, 3, only 3 minus is left out. This is easy to understand. So central metal ion is Fe3 plus, whose electronic configuration is D5. How do we know that is a 3,5? D5. Actually, Fe electronic configuration 3D6 4s2. Whose electronic configuration is this Fe? Fe metal atom has 3D6 4s2 electronic configuration. If you knock out 3 electrons from it, 2 from S, 1 from this. So when you remove 3 electrons out, we have 3D5. That's why it is 3D5. Because as the tripositive, 3 electrons from the iron atom is removed and resulting to 3D5, resulting in 3D5. So 3D5 electronic configuration is supposed to be how much? How D5 means this is how all the here 1, 1, 1, 1, 1. 5 electrons would be separate, independent, unpaired. But what happens here? The cyano group, which is a powerful ligand, magnetic field ligand, which pushes up all the odd electron, trying to maximum pairing up occurs and resulting to 2 paired electron and 1 odd electron. This is easy to understand. 5 orbital, 5 electron. All the 5 electrons are 1, 1, 1, 1. Okay, this Cn minus, what does it do? Push up all these odd electron inside and maximize the pairing. 2 paired electron, 1 odd electron. There is no other way. and thereby keeping 2 d orbitals vacant, and takes another 4 orbitals from the next higher energy level, say 4s1 orbital, 4p3 orbital. Put together, 6 vacant orbitals are made available by the action of Cn minus. Because it is a strong field ligand, it can push up, it can manipulate the electronic configuration of 3D orbitals and thus giving rise to this structure. Okay, so now these 6 orbitals are mixing up together and forming a new set of orbitals called D2sp3. These D2sp3 6 orbitals orient in space such that they occupy the vertices of regular octahedron. How many vertices are there? 6 vertices are there, and thereby the shape becomes octahedral. Okay, and we have got only one unpaired electron. Otherwise, it is supposed to have 5 unpaired electrons. So only one unpaired electron is there. Still, it is paramagnetic. Even though it is a magnetic moment is less, it is a paramagnetic compound. Okay, what are the things to know here? Its name is hexacyanoferrate 3. Instead of calling it as iron, we say ferrate because it is in negative ion, anion. Okay, the next, the central metal ion charge is 3 positive. How does this 3 positive come? 3d6,4s2 is the neutral metal Fe electronic configuration, from which 3 electrons are knocked out, and thereby Fe3 plus is formed. So 3 plus has 3d 5 electrons. The ligand is cyano, whose sign symbol is En minus. The electronic configuration of the hybrid orbital is this. In the 3d5 orbital, 3 orbitals are having 5 electrons of the iron. The other 2 3d orbitals are used up for hybridization and giving rise to D2sp3 6 orbitals. These 6 orbitals are filled by the pair of electrons supplied from Cn minus. Each Cn minus give one pair of electron to this D2sp3 orbital and giving rise to this complex called octahedral complex called FeCN63 minus. This is all about you got to know here. Shall we go to the next one? This is again iron complex whose coordination number is 6. Hence 6 fluorine ion join. Okay. The central metal ion is Fe3 plus. Again the same manner, Fe3 plus combined with the 6 minus groups and giving rise to 3 minus outside. So out of the 6 minus, only 3 minus is left. The 3 minus is balanced by iron. 3 minus is balanced by iron in the sense Fe3 plus. Fe3 plus in the sense it is 3d5, the same explanation given in the previous example, 3d5. Okay, those 3d5 5 electrons are the same way. All the 5 d orbitals are occupied by 1 odd electron each. Okay, now a very weak ligand F minus approaches. As the F minus approaches this central metal ion, it cannot do any manipulation in the 3d orbitals, and it takes the next 6 vacant orbital, say 1 s orbital, 3p orbitals, 2 4d orbitals, and thereby mixing up sp3d2 6 vacant orbitals in the next higher energy level are put together, forming sp3d2 hybrid orbitals. Again I say All these 6 orbitals are alike, similar in shape, size, and energy. That's why we call them as degenerate orbitals. These degenerate set of 6 orbitals repel among themselves and they stand maximum apart from each other, giving rise to regular octahedral shape. These in the regular octahedral shape, there are 6 corners. Towards each 6 corner, these 6 orbitals move apart from each other. They stand along the corners towards the corner. See, one sp3d2 orbital stand along the one corner this way, one the other corner here, this corner, this corner, this corner, and 6 corner. All the 6 corners, when we join together, we get the octahedral shape. This octahedral shape is due to the hybridization. This particular hybridization sp3d2. Okay, sp3d2 gives rise to octahedral shape to this complex molecule. Okay, now we come back to the unpaired electron. There are 5 unpaired electron, maximum number of unpaired electron. Due to the presence of maximum number of unpaired electron, it is a strongly paramagnetic compound. Strongly paramagnetic component. 5 unpaired electrons are there. We can easily find the magnetic moment, dipole moment in this molecule. Strongly paramagnetic compound. This is a strongly paramagnetic compound. Okay, now come from the beginning. Its name is hexafluoroferrate 3 ion. We call it as ferrate instead of ion because of anion. When a metal is inside an anion, we call it like this: nickelate, ferrate, cobaltate, and so on, not their name as it is. This bracket third or 3 refer to the charge on the metal ion. That's it. The formula is this: central metal ion is iron 3 plus. Its electronic configuration is the 3d5. The ligand is fluoro F minus. Since fluoro F minus is a weak ligand, it can't do anything with the 3d5. Therefore, 3d5 orbitals are occupied with one electron each, giving rise to 5 unpaired electron, strong paramagnetism. Next, due to the weak magnetic field, it takes up the next higher energy level, sp3d2 orbitals, and this hybridization giving rise to the octahedral shape. And sp3d2, and this is an outer, again it is an outer orbital complex. We call it as an outer orbital complex. Outer orbital complex, not inner orbital complex. This is all the information we will have to know about this particular example. Now we have come to another example. Here we have another metal, manganese, Mn, surrounded with 6 cyano. Its coordination number is 6. Its coordination number is 6. Okay, the metal atom, again, its electronic configuration of D5. 3d5, 4s2 is the electronic configuration of Mn. Metal Mn, electronic configuration is 3d5, 4s2. But Mn 3 plus, Mn 3 plus is different, How do we get 3 plus? We will have to remove 3 electrons from here. 2 electrons from s orbital, 1 electron from d orbital, and thereby we have 3d4 orbitals. It has a 3d4 electrons. The 3d shell, we have only 4 electrons because of this reason. So Mn 3 plus ion, electronic configuration is the 3d4. And the ligands present here, cyano, Cn minus, which is a strong field ligand. This strong field ligand, what does it do? the 4 electrons here. Normally, the electronic configuration of M1 4 is this. The 4. Another electron is here is vacant. What does it do this thing? Cyano is capable of pushing the electron inside and pushing the electron here. And resulting okay, this is so. Can push. This can occur. Can push, but it does not do. This is an exception. This does not occur. Because if it does do, no, 4d orbital cannot take part in the 4d orbital cannot take part in this hybridization. That's why it simply leave it, even though Cn minus is capable of doing manipulation strong field. But even though as an exception, it does not do. If it does like this, what happens here? In the d orbital, there will be 4 vacant orbital. When d orbital 4 means it needs so such a mixing up, such a hybridization is not possible energetically. That's why what does it do? Simply leave it and takes the arrangement in a different way. We shall see it again here. I do it again, 1, 2, 3, 4 are there, no? Only one electron is used for pairing, resulting to this type. The other 2 electrons are left because it wants only 2 d orbitals. Shall I explain again? Instead of pairing all the electron, it does a pairing work of only one electron is pushed inside and leaving the other 2 electrons, and it takes only 2 d orbitals. Because for d2 sp3 hybridization, it requires only 2 d orbitals. By pushing just one electron inside, 2 d orbitals are made available. That's why this type of arrangement takes place and resulting 2 d orbitals, 1 s orbital and 3 p orbitals mixing up together due to sp3 hybridization has occurred. Okay, 3 possibilities are here. 1, pairing up of all the 4 electron. Other, pairing up of only one. Other, leaving the unpaired electrons as it is and going to the next shell. Cn minus being a strong field ligand, it chooses this option. What is this option? Only one electron is pushed in, not. If at all, I want to just to make it, in elaborate, because this requires some explanation. This is first shell, first orbital, second orbital. See, 1, 2, 3, 4. This is actually this is 3D 4. Okay. Now the Cn minus want to do any type of manipulation inside the 3d orbital, and it wants to have only 2 d orbitals vacant. For getting 2 d orbitals, only 2 orbitals vacant, it simply pushes one electron here and giving rise to this configuration. It doesn't bother about the next inner orbital, whether it is unpaired or paired. It wants only 2 vacant orbital. So this is what happens here. Why I say again and again here, this is a peculiar case. Even though cyano is a very strong field ligand, the compound is paramagnetic. There are 2 unpaired electrons. The 2 unpaired electrons are left without anything by the strong field because of this reason. This reason you will have to understand. Here the question, many times they ask, M1Cn6 minus complex is paramagnetic, even though cyano is a strong field ligand. The reason is this: D4, instead of complete pairing up, only partly pairing up takes place and two unpaired electrons left out because the cyano group wants only two vacant orbitals for hybridization. That's why it happens and resulting this type of hybridization, and two unpaired electrons are left out. Now you understand? Two unpaired electrons are left out and thereby it is a paramagnetic yet. And its hybridization is D2 sp3. And this is the representation, and it is an inner orbital complex. Inner orbital complex because no 3D orbital, two 3D orbitals are made used up. Okay. Again, the only point to remember here in this example, 4D orbitals giving rise to sp3d2 hybrid orbitals. 6 such orbitals are mixed up together and new set of 6 orbitals are formed. All these 6 orbitals are equal in energy, size and shape. These sp3d2 set of orbitals repel each other and resulting to octahedral shape. Each one occupy the corner, which is vertex of octahedron. Okay, and giving rise to this coming. So, what are the things to say here? Cl minus a weak field ligand. There are 4 unpaired electrons left as it is, and thereby it is a strongly paramagnetic compound, and its hybridization is sp3d2 and shape is octahedral, and it is again outer orbital high spin complex. High spin because 4 unpaired electrons left. This is a good example of high spin complex, and we have discussed enough number of examples.